Hello, my name is Vinicius and I'm going to present the work Mass Flow Prediction in a Refrigeration Machine using Artificial Neural Networks, done by me and Antonio Maia. The commercial and domestic refrigeration systems with on-off controllers have poor temperature control, limited operation conditions, and reduced lifetime. The use of control systems becomes increasingly interesting to reduce energy consumption and allow it to obtain the desired temperature more quickly. To develop this control system, it is necessary to build a mathematical model of the refrigeration system, which often requires knowing the mass flow of the refrigerant. The measurement with a flow meter has a high cost with installation and maintenance. In addition, it is also invasive and often sensitive to vibration and magnetic fields, which can hinder a correct measurement. The artificial neural networks, ANN, are commonly used in refrigeration systems to predict many parameters. In this study, the objective is to correlate mass flow rate values with other quantities more easily observed during the operation of the refrigeration machine. So, the mass flow could be accessed indirectly from easily measured quantities and at a low cost. With the use of ANNs in this study, it is possible to correlate mass flow values with other quantities more easily observed during the operation of the refrigeration machine. On the contrary of other studies, which used even 6 different parameters as inputs, this work will try to use as little as possible. So, the objective of the work is to predict the value of the mass flow in a refrigeration machine indirectly, from the correlation of few easily observed parameters using artificial neural networks. This flowchart shows the work methodology. The first step was to collect the experimental data, doing many tests in different operation points. After the system was operating, a valve was partially closed to restrict the mass flow rate, so it was possible to obtain transient response data until the system stabilized again. After that, the evaluation of the mass flow rate was done to decide which parameters would be used to predict the mass flow rate. The decisions were made taking into consideration the mass flow rate estimation equation. Decided the inputs and outputs of the ANN, the data passed through a pre-processing stage where it was cleaned and normalized. At last, the ANN loop started. First, the ANN was developed using Python and Keras library, and the hyperparameters were optimized. With the results of the optimization, the training could start, and after the training, the validation was done. Depending on the results of the optimization and the validation, the ANN could be changed, so the development of the ANN had to restart. The experimental device used is presented here. This device consists of a vapor compression refrigerant system that uses R134A as the refrigerating fluid and as secondary fluid pure water in the evaporator and condenser. The system comprises a reciprocating compressor, a condenser, a subcooler, an evaporator, 3 expansion valves, and systems to perform measurements and data acquisition. The operating points employed in this study correspond to 650 and 750 rotations per minute. 11 T-type thermocouples were installed inside the tubes at the inlet and outlet of each system component to measure the temperature. The refrigerant mass flow was measured with a Coriolis flow meter. The experimental data were collected for several different permanent and transient regimes, considering 4 evaporating temperature from -5 to 10 degrees Celsius and 2 compressor speeds, 650 and 750 rotations per minute. To decide the inputs for the ANN, with the objective to predict the mass flow rate, the equation of the mass flow rate estimation was considered. It is possible to see that the mass flow rate depends directly on the compressor rotation, compressor displacement, specific mass at the compressor inlet, and volumetric efficiency. The volumetric efficiency depends on the condensating and evaporating pressures. The pressures are thermodynamically related to the temperatures. So, for the inputs to the ANN was considered the specific mass, the condensate temperature, and the evaporating temperature. The specific mass at the compressor inlet was estimated using this equation, taken from a study made by Cleland in 1986. With it, it's possible to calculate the specific mass using only the superheat, the evaporating temperature, and the vapor specific volume. This makes this work more viable. So, only from the temperature measurements it is possible to achieve every input necessary for the ANN model. The data passed through a pretreatment stage to eliminate outliers that were polluting the measurements. The technique chosen to mitigate the outliers was Ettman's Z-score formula. For every point, the Z-score was calculated. If the value was above 1, this point was considered an outlier, and it was substituted by the local average. The data also had to be normalized to go through the ANN. This was done using the standard normalization equation, so every data was in a range of 0 to 1. The ANN model used in this work was a multi-layer perceptron, where all inputs are multiplied by the ANN weights and summed to get to the neuron result. This process is done until the output result is obtained. The model of the neural network was made using Python programming language and the Keras library. The hyperparameters were optimized using a hyperband algorithm, which is a variation of a random search, but using adaptive resource allocation and early stopping. The hyperparameters optimized were the number of layers, the number of neurons, the learning rate, the dropout rate, and the activation function. Two different cases were considered. In the first one, the data from the steady state and transient responses were used in the training. Then, in the second one, only the data from the steady states were used in the training. The main reason to do it is to evaluate how the ANN will behave and to verify if the ANN model can predict transient data with only permanent data in the training. This graph is an example of how was the data from the experimental bench. It is possible to see that the refrigeration machine was in a steady state, and to generate the transient response data, the mass flow rate at the inlet of the evaporator was reduced in about 5% by manually closing the manual expansion device. Then, the dynamic system response data, due to this disturbance, were collected and stored in a data file until the system achieved a new steady state. The data were divided 70% for the training, 15% for test, and 15% for the validation. Also, 2 operation points were left out of the training to be used as validation for the model, to verify if the ANN can predict a completely new operation point after the training. So, there were 2 validations in this work. The first one was the training validation with the 15% of the data, and then the second validation predicting 2 new operation points. These graphs show the comparison between the original noisy data and the cleaned one. It is possible to see that the application of the Z-Ettman score formula was successful to obtain a cleaner and smoother data. This table shows the hyperparameters local best setup. As a result of the hyperband algorithm search, the hyperparameters chosen were for the activation function the hyperbolic tangent, the optimizer was Adam, the number of hidden layers were 3 with 32, 26 and 10 neurons, and a dropout ratio of 0.01. This graph shows the mean squared error evolution during the training and validation. All the training were done until the average error wasn't improving as much as more epochs were done to prevent overfitting. In every scenario, the mean squared error achieved was really small. This graph shows the results of the first validation of the network using permanent and transient data in the training Even though the maximum error is relatively high for 750 rotations per minute, which is 4.76, the average error was significantly small in both cases, with 0.07% and 0.44%. These two graphs show the results of the prediction of completely new operation points for the model. For the 750 rotations per minute, the result was worse, but in both cases the predictions were close and with a small average error of 0.23% for 615 rotations per minute and 0.56% for 750 rotations per minute. Now the results with only permanent data in the training. Again, in both graphs it's possible to see that the validation results were really close to the previous case. In the first validation, the average error was small for both rotations, 650 and 750 rotations per minute. For 650, the average error is 0.012%, and for 750, it's 0.39%. For the predictions of a new operation point in both rotations, the ANN predictions were really close from the expected data. The average error for 650 rotations per minute was 0.092%, and for the 750 rotations per minute is 0.24%. So the most important thing about these results is that every average error was smaller than the mass flow rate prediction uncertainty of the experimental bench. To conclude this study, the data were collected from 80 different operation points, including transient response data. The specific mass, evaporation, and condensation temperatures were used as inputs for the model. The ANN used was a multilayer perceptron with hyperbolic tangent as the activation function and Adam as the optimizer. For each rotation, two forecasts were made. In all of them, the average error was very low and under the experiment uncertainty. For the ANN strain with steady-state and transient response data, the maximum error was 4.71%. For the ANN strain with only steady-state data, the maximum error was 3.81%. Considering that in every case the average error was really small, it is possible to conclude that the ANN model can fairly represent the refrigerant fluid mass flow rate. The error with only the steady-state data in the training being smaller shows that if the ANN has information about two close steady-state conditions, the transient response in between is not necessary for forecasting the mass flow rate. Thank you for your attention.